So I would like to welcome you all to this webinar session on next generation crustal stress maps and their utility for understanding induced seismicity and active tectonics. The speakers of today's talk is Dr. Jens-Erik Lund Snee, Mendenhall Research Fellow, United States Geological Survey, USA. I came to know about him from my batchmate and a good friend, Mr. Partha Pratim Bandal, who is right now available among audience for this talk. So before I go any further, I would like to read his brief biodata that he sent to me. Jens-Erik Lund Snee is a Mendenhall Research Fellow at US Geological Survey. Dr. Snee is a geologist and geophysicist who studies tectonics and geomechanics at a range of scales. He received his PhD in geophysics from Stanford University, where he worked with Mark Jobeck to develop a new generation map of the state of tectonic stress in North America, with applications to induce seismicity, continental dynamics, and oil, gas, and geothermal energy development. Dr. Lund Snee received his MS in Geological and Environmental Sciences from Stanford, where he and Elizabeth Miller studied the tectonic and paleogeographic history of the Great Basin in the Western USA. He was previously awarded a Fulbright Fellowship to study the Alpine Fault Plate Boundary System in New Zealand, and his experience includes work for Statoil, which is now known as Equinor, as a hydrocarbon exploration geologist in the deepwater Gulf of Mexico and for the US Forest Service. With this, I would like to request Dr. Lund Snee to start his talk. Thank you so much.
Thank you. Thank you, Professor Agarwal and Partha, for inviting me. This is my first time speaking to an IIT, so that's fun. I guess it's evening there. And I will be talking about some of the things that you just heard about. I'll be talking about the next generation stress maps that I've been developing, published the first one for North America in 2020. This will be a very USA-centric presentation, and I hope that it's at the appropriate sort of level for all of you. But if something is really confusing, please just stop me or send a Q&A or something, and you know, I can hopefully sort it out. Okay, I'm going to start by talking about the stress mapping that we've done and are continuing to do, and I'll talk about the methods, how we develop the maps, and what they show. This is the work has been done for the continent of North America. Then I'll talk about applications, first for induced seismicity, and then for understanding geodynamics, specifically sources of stress. Okay, about the stress mapping. To get us all sort of on the same page, this will be familiar to many of you. The style of faulting that's active anywhere in the Earth is controlled by the relative magnitude of the three principal stresses. So there's usually one of the principal stresses is typically close to vertical, and so that means that the other two are usually close to horizontal. And that's quite convenient because that means that we have a vertical stress and then the maximum horizontal stress, the minimum horizontal stress, SH max and SH min. And simply by knowing the ratio between those three, we know whether normal faulting, extensional faulting is occurring, strike-slip faulting. That's, of course, side-to-side faulting, where the vertical stress is the intermediate principal stress, or reverse compressional faulting, where the vertical stress is the least principal stress, allowing blocks of rock to move over one another. And so all you really need to know to understand which faults are going to be active in a particular area of the many different faults that exist in the crust, which are going to be the ones that are most active. See, I have a question here. Yes. Is all you need to know is the relative magnitude of those three principal stresses and the orientation of one of the two horizontal principal stresses. And we usually, by convention, show the orientation of SH max on the maps. So we have several reliable ways at this point to measure SH max orientations. This is sort of the main one that's used in industry. I would say most often, we're looking at borehole image logs. These are from subvertical boreholes. These are views of the image logs. If you haven't seen these before, it's unwrapped. So we have the compass directions, northeast, south, west, and then north again. And in this case, there just happened to be both drilling-induced tensile fractures, which are these fine lines, and borehole breakouts. And so the drilling-induced tensile fractures are 180 degrees apart on either end of the wellbore. And those, where they do form parallel to SH max. So that's convenient. And these dark zones, borehole breakouts, form parallel to SH min or perpendicular to SH max. It just so happens that both are present in this well, although you could have either one or neither of them as well. So with enough of these in a single borehole covering enough vertical distance, with enough consistency in their orientations, we can obtain a reliable measurement of SH max orientation. And we apply quality ratings, which is important so that we know, which measurements are good enough to be put on the map. This is used frequently, but there are many other techniques that are also reliable, one of which is the use of earthquake focal mechanism beach balls, like we're seeing here. You can see that not only do they contain information about the maximum horizontal principal stress direction, but they also contain information about the style of faulting or relative magnitudes of the three principal stresses. So normal faulting earthquakes occurring in an area tells you that normal faulting is active there, for example. And SH max orientations can't be determined from a single one of these. It's just not, there's just too much uncertainty for single focal mechanisms. But if you have enough of them, say 20 or more in an individual area, they can be inverted to determine the best fitting state of stress that gave rise to all of those earthquakes. And so that can give you precise values for both SH max orientation and relative stress magnitudes. And so this is used where there are a lot of focal mechanisms available. And this is a new technique that we've started using in the era of multi-stage hydraulic fracturing of subvertical or horizontal wellbores. And so we're looking at a map view here of a fracking operation that was done on this middle well. And this is an old data set, but you can still see that there are aligned groups of these dots, which are microseismic events. And in most cases, these represent the cloud following the hydraulic fracture that is forming perpendicular to the wellbore. And in most states of stress, they'll form in the direction of SH max. So if we measure enough of these aligned groups of events, we can obtain a good SH max direction. And there are several other techniques, but I'll just move ahead to talk about the new mapping and what it shows, and that's what's here. We're calling this a new generation map of the state of stress, and I'll explain why in a minute. But first, I want to explain some of the things that we see here. So the black lines represent the orientations of SH max. Most of these are from the world stress map, but we've added a few hundred new ones, predominantly in the central and eastern United States. You can think of each of these lines as a measurement from an individual point, say a wellbore or a hydraulic fracturing operation or a place where focal mechanisms were inverted. And the orientation of that line represents the orientation of maximum compression. And the length of the line corresponds to the quality of the data. So longer lines are higher quality data, and we're not showing data that are unreliable on the map. Okay, so you can see already trends apparent in these orientations. For example, in the eastern part of the continent, SH max is more northeast, southwest, and then there's a gradual rotation westward into the central parts of the continent. I'll be talking a lot about Oklahoma and Texas shortly from an induced seismicity point of view. But I also want to talk about the colored background here, and that's really the aspect of this that makes this a new generation map, because in the world stress map, prior stress mapping, SH max orientation is almost all the information that you have available. But what we're doing here is that we're mapping the relative stress magnitudes, so the style of faulting, but we're doing it quantitatively using what's called the Aphe parameter. And let me, let's see. I'm in trouble advancing this slide. I don't know why. Sorry, let me try this one more time.
Yes.
Okay. Share screen. Okay, hopefully you can see that. So the Aphe scheme is illustrated here with some different types of the style of faulting that is possible in the Earth. The Andersonian faulting styles that I mentioned earlier are shown here in the center column, where we have normal, strike slip, and reverse faulting. And this Aphe value is mapped onto the styles of faulting that are possible. So the value ranges from 0, which is the most extensional possible state of stress, to 3, which is the most compressive, and anything in between can be seen. So this number varies smoothly between those values. And so normal faulting, for example, pure normal faulting would be an Aphe of 0.5. Strike slip faulting is more compressive, so that's an Aphe of 1.5, and reverse faulting is 2.5. But there are additional states of stress that are possible as well if we go beyond the sort of Andersonian style that we're used to seeing. So radial extension is the most extensional style of faulting, and that's just where the two horizontal principal stresses are about equal and the vertical stress is greatest. That would be an Aphe of 0. Normal and strike slip faulting can occur at the same time. That doesn't mean necessarily that there's a complex stress field. It could just mean that the vertical stress is more or less equal in magnitude to the maximum horizontal principal stress. And note that because this value varies smoothly, there's a whole range that's possible here between 0.5 and 1.5 of increasing amounts of strike slip faulting relative to normal faulting. And so on. We can have strike slip and reverse faulting and radial compression as well. And so if we go back to looking at the map, we see these areas that are, that are cooler colors. So the bluer colors here in Western US and parts of Mexico, for example, are areas where there's the more extensional states of stress. So the teal color is both normal and strike slip faulting at the same time. Much of the western part of the continent is that style of faulting. You can see these more blue areas. Those are pure normal faulting areas, sort of rift environments like the Rio Grande Rift here. But further east, we get more and more compressive states of stress with strike slip faulting in green in places like Oklahoma and further east, strike slip and reverse faulting in orange here, and then much of the easternmost parts of the continent are red for reverse faulting. And I should say that the way that we obtain these values is where we have a lot of focal mechanism data, which is, usually in the western part of the continent and a few scattered other areas. We can do focal mechanism stress inversions and obtain very precise values of Aphe, but we don't have focal mechanisms everywhere. And so in a lot of cases, what we do is we measure, we make interpretations on the basis of individual focal mechanisms or small numbers of them. So for example, in an area, if you're seeing both normal and strike slip faulting focal mechanisms, let's say there's a handful of them, you know that you're somewhere between normal and strike slip faulting. And then with more and more information, you can narrow that range. But the bottom line is that there's an uncertainty associated with all of these, and we've mapped that as well. Okay, so to move on, I want to make a couple of points about the stress mapping. Now that we have done so much of this work, there's some important learnings here. And the first is that the stress field is coherent even in places where it is very complex, like Texas, for example. And so here's the state of Texas, and there's Oklahoma, which we'll be talking about later, and Mexico down here to the southwest. And we're blowing up the Permian Basin, which, as some of you may know, is probably the most important oil and gas producing region, at least onshore in the United States. And you can see that the state of stress is actually quite complex here. We have slightly more compressive states of stress to the east, so that strikes up at normal faulting in what's called the Midland Basin here. But SH max is close to east-west, maybe east-northeast, west-southwest, and there's sort of a rotation to northeast-southwest as you move out of the Permian Basin to the east. But if you go to the west, not only do we have close to pure normal faulting, but there's this remarkable rotation here, 150 degrees clockwise southward or so. And you can see it because we have so much data. Almost all of these data are new from the past few years, contributed largely by the oil and gas industry. And the point here is that if we had a tenth as much data, it would look chaotic and you might not have any idea what the state of stress really is and what you could trust, and it would look incoherent. But because we have so much data, you can see that the stress field tends to vary in a smooth manner. Another important point is that we are looking at data from several different stress indicators. So not only the wellbore types that I mentioned, but also aligned microseismic events that I mentioned, focal mechanism stress inversions, depending on the style of the line, are all showing roughly the same thing in the same areas. And importantly, you can see some of the earthquake focal mechanisms here. Their nodal planes, or the strikes of the nodal planes, rotate in accordance with the SH max orientation. So these are normal faulting earthquakes, and the strike of those normal faults change across the basin based on the SH max orientation. And that's important partly because the earthquakes tend to be occurring here in areas much deeper than the wellbore measurements were made. Those wellbore measurements of SH max orientation were made in the sedimentary rocks where oil and gas development is happening, and most of the earthquakes are happening in the crystalline basement. Some of these, by the way, are induced earthquakes, and I'll get to that a little later. So to talk about induced seismicity now, the applications of knowing the state of stress in areas where induced earthquakes are happening or possible is that, first of all, we can determine which orientations of pre-existing faults are the most likely ones to fail as a result of some kind of perturbation, usually an increase in fluid pressure due to disposal or hydraulic fracturing. And we can also look back on prior earthquakes and determine what the likely causal mechanism was for that earthquake. Now, I'd like to motivate this by pointing out a major challenge that we're all facing in just the next few years. This is an analysis by the International Energy Agency from a couple of years ago, and this will probably be familiar to many of you. The idea is that in order to keep warming to about 1.5 degrees Celsius, we're already most of the way there, we need to reach global net zero emissions by 2050. So that's a very tall order. As IEA said, that will require nothing short of the complete transformation of the global energy system. So the job for geoscientists is impressive, and there will be a great deal of work for all of you, all of us, coming up, more work than I think we can possibly handle. And that's illustrated here. There's sort of two technologies that are especially relevant to geoscientists for addressing the climate change problem. One of which is carbon capture and storage, or carbon capture utilization and storage. And the other is geothermal energy development, which I'll talk about. The problem is that both of these are associated with induced seismicity. And another problem is that we have to drastically scale up our development of both of these technologies. So if we look at today, we're putting a very small amount of carbon underground, about 0.04 gigatons per year worldwide. And to meet the IEA's sort of model for achieving net zero emissions, carbon capture and storage is critical, and they estimate about a 20 times increase in storage is required by 2030. So all the operations, the carbon storage operations that exist now are tiny in comparison to what we need in just the next 8 years. Something similar is true for geothermal energy. It's not quite as critical to meeting the net zero carbon emissions goals, but it is part of the picture. And it's the challenge is apparent when you see how little geothermal energy is being produced right now globally. About, let's see, well, 94 terawatt hours anyway in 2020 worldwide. And we're going to need to multiply that by about 3 by 2030 to be an important part of the electricity generation picture. And as you can see now, geothermal energy is a small slice just of renewable energy sources. So it's really a very small player right now, but needs to be much bigger. And that makes this problem of induced seismicity especially stark, because what we're looking at here are earthquakes in which geothermal energy development is suspected to have been the cause around the world. So just with a very small amount of geothermal electricity generation that we have right now, we have earthquakes in some cases quite large ones, like in Pohang, Korea, a few years ago, and you know, but we need to scale this up by about 3 times within the next 8 years. Carbon capture and storage represents only a few suspected earthquake locations. You can see 2 of them here including one in the Decatur site in Illinois in the US. But remember that we need to be increasing our carbon storage by on the order of 20 times. Not all of that will probably go underground, but still a huge increase in storage needed. So the induced seismicity problem is going to be one that we need to tackle. And just to underscore why it's so important to focus on the induced seismicity problem, I want to point out one of multiple cases where an enhanced geothermal energy development site was shut down due to a loss in what you call the social license to operate because it triggered earthquakes. This is one of the early ones in Basel, Switzerland, where you can see about 6 days after they started injecting water underground to stimulate a reservoir for bringing hot water up towards the surface. Over time, so the bottom is earthquakes, the top is wellhead pressure in black and flow rates in red. And you can see they started pumping. Wellhead pressure was 0 at first, and they pumped very aggressively within the first few days, got up to 30 megapascals. And then you can see the earthquakes just started from almost the beginning, took off, and they realized they had a problem. They shut in the well. And right after that, they had a magnitude 3.6, I think, earthquake, which is not a particularly large earthquake, but some places are more sensitive to seismicity than others. Basel had been destroyed a few hundred years ago by another earthquake. And as people like to say, the memory in Europe can be very long. And so the operation ended, and a few years later, so this was done in 2006, a few years later, not only had the operation been shut down, but it ended up being permanently shut down. And in this case, the operator ended up facing criminal charges. They were dismissed eventually, but this is to underscore the importance of this problem. Okay, well, an important principle to keep in mind relative to this problem is that the crust is, we expect the crust to be critically stressed basically everywhere. And this helps explain why we have induced seismicity in so many parts of the world occurring just from these small developments in the case of Basel, for example. And what I mean by that is that pretty much everywhere we expect, in the brittle upper crust, we expect the best oriented faults to be about 1 earthquake cycle away from failure. So as tectonic activity is loading the crust, it increases the differential stresses, or the difference between the maximum and minimum principal stresses, and movement on faults releases that over time, but it goes over and over and over again over the course of geologic history. And so we can see both in deep boreholes, like we see on the left here, that the ratio between the maximum and minimum principal stress is what you would expect from the stresses being modulated by the strength on the frictional strength of the best oriented faults. So there's a coefficient of friction of about 0.6 is what we tend to think of as in terms of fault strength, and that's what we see. Another piece of evidence is the occurrence of reservoir-induced seismicity, even in very stable areas. So I'm showing both the eastern parts of the US and Southeast Canada on the left here, and parts of Asia here on the right. And in both cases, the black dots represent seismicity, and the red circles are cases of suspected reservoir-induced seismicity. And so these are cases where a reservoir was impounded, and in many cases, a major earthquake occurred. A number of them have happened in India. They've been very destructive, Eastern China as well. And it's important to recognize that these are very small, these are caused by very small changes in the stress field. It's just water being added to the Earth's surface. But these areas were critically stressed. Those faults might not have failed for another 100,000 years, but that small amount of stress perturbation caused them to fail. So I want to make a side note before talking more about induced seismicity, and that is that using this principle of the crust being critically stressed is quite powerful. One of the things we can do with it is estimate the absolute magnitudes of the principal stresses using this Aphe value. Somebody's asking about if there's any critical magnitude of earthquake above which is considered serious. It depends a lot on where you are and what the building construction looks like. We can talk more about that shortly. But so what I'm showing here is that is a plot of the stress magnitudes in megapascals as a function of the style of faulting Aphe. And so, and these are normalized to the vertical principal stress. So the vertical stress is just controlled by the weight of the overburden in a particular area. So you can think of the vertical stress as being representing a particular depth. So for any area at a particular depth, if the style of faulting is more compressive, you can see how SH max and SH min increase characteristically. And so there's some assumptions associated with this, but in this new paper in AAPG Bulletin, the equations are laid out. And there's a calculator on my website that you can use to go from Aphe to at least estimates of absolute stress magnitudes, assuming that the crust is critically stressed. Okay. Now back to induced seismicity. This is the general framework for how most induced earthquakes occur. Most induced earthquakes are triggered by increases in fluid pressure. And this is for the oil and gas context, but it could be applied to geothermal as well, or carbon capture and storage. Water produced along with oil and gas is typically very toxic. It needs to be disposed of in some way, and usually the easiest way to do that is to re-inject it deep, well below the drinking water aquifers. And that's perfectly fine up until the point where the pressure associated with that increase and with that disposal reaches pre-existing faults. In some cases, if those pre-existing faults cut down into the crystalline basement, they might be very large faults. That's where you might find the largest ones. And larger faults allow for larger earthquakes. And so this has become one of the main problems in the United States for induced seismicity. Hydraulic fracturing operations, both oil and gas and enhanced geothermal, can trigger earthquakes because they're injecting very high fluid pressures underground. And if there is a fault right there in the operational area, that fault can be made to fail as a result of that increase in fluid pressure. And water flow back from hydraulic fracturing fluid is often injected deep to dispose it as well, and that can trigger earthquakes too. So this is the general framework for how most induced earthquakes occur. And we can think about this in a mechanical way. I realize that not everybody knows or likes Mohr circles. You don't have to know them well in this case. But the point here is that if the crust is critically stressed or close to being critically stressed, that means that the best oriented faults, which would be this red dot here, are within about one earthquake cycle of failure anywhere in the crust. And so the failure, and that's what's depicted in the sense that here the failure line is this black line. Any one of these dots is a fault of any orientation, shown kind of randomly and schematically here. A Mohr circle, or these Mohr plots, are simply a plot of shear stress as a function of normal stress in a particular state of stress. So here, this is a case where the SH max is slightly greater than the vertical stress. So that's a sort of strike slip normal faulting state of stress. And most of these faults are far away from the failure line, but there are always some that are close. And they'll just fail over and over again in geologic time. If pore pressure increases, say due to wastewater disposal or hydraulic fracturing, you can think of the Mohr circle as moving to the left, or equivalently, the failure line moving to the right. And more faults become potentially active, and then you might have an earthquake occurring on one of them. And if you know the stress field, as you do in this schematic case, and you know the orientation of the fault, you can estimate the pore pressure that would have been needed to trigger slip on that fault. Or you can think about it in advance of a problem and say, well, we know there's a fault of this orientation. How much pore pressure do we think that fault can handle? Is it safe or not very safe? So we've applied this analysis in a number of cases. Back to the Texas area here. We've done this in several places. I'll just focus on this one example of Azle near the Dallas and Fort Worth metropolitan area here in Northeast Texas. This is in the Fort Worth Basin. It used to be a major source of natural gas development. And in this case, they were injecting wastewater down into the sort of lower parts of the sedimentary succession. 2 earthquakes occurred, and we got focal mechanisms for both of them, or I didn't, but others obtained focal mechanisms for those. And Mark Zobak and I estimated the state of stress in this area and how much pore pressure increase would have been needed to cause failure on either of these faults. And we found that they were extremely well oriented for failure, and in fact, very little pore pressure. We're talking, much less than a megapascal for one of the fault planes would have been needed to make it fail. And in fact, this is what we're seeing in many cases. It appears that in general, a lot of the induced earthquakes that have occurred, at least in areas of wastewater disposal, seem to be occurring in response to very small changes in pore pressure. We can test this on a more grand scale in Oklahoma. So this is just northeast of where we were just looking before, or just north, Texas down here to the south. This is an area where literally thousands of magnitude 3 earthquakes and greater occurred in recent years. Before that, it had had extremely low rates of seismicity, but because of wastewater disposal, and in some cases, hydraulic fracturing, enormous increases in seismicity occurred in the sort of mid-2010s, and then decreased a little more gradually than that as wastewater disposal volumes decreased more recently. And so these are the earthquakes here, colored by the time, and the dot size is scaled by the magnitude. And so hundreds of magnitude 4 and greater. And in these cases, I don't think anybody was badly hurt by these earthquakes, but certainly there were some injuries and there was a lot of damage to structures. And I mention these partly because the pore pressure modeling in these areas, so people have attempted to model the increase in pore pressure at the seismogenic depths. In this area, the earthquakes are mostly happening in the basement, so this is for about 6.5 kilometers depth. And if you take all the record of wastewater disposal into disposal wells all across this area, and then you try to model the increase in fluid pressure, the model results suggest very minor increases in fluid pressure associated with all of these earthquakes, right? So we're seeing pressure increases in the black areas up to about 0.3 megapascals, which is really not a large increase in pore pressure for 6.5 kilometers depth. But I'll note that these are very simplistic sorts of modeling exercises. They're not accounting for things like faults being more conductive to fluids than the bulk earth, which will be less conductive to fluids, and so on. So we can test this by looking at the orientations of faults in the stress field. And this has become possible more recently because we, through the advent of machine learning-based earthquake catalog detection methods. And this is a new one right here by Young-Soo Park, Bill Ellsworth, and Greg Baroza at Stanford. It includes a very impressive more than 300,000 earthquakes. We're looking again at the same area of northern Oklahoma and southern Kansas. And what they've done is they've developed a deep learning method to detect earthquakes and then pick the P&S arrivals from that. And then the earthquakes are relocated using the HypoDD algorithm. And we end up with an extremely detailed catalog of earthquake locations. And so from that, we can determine the orientations of the literally thousands of faults that failed in this area. And so here's, I've been manually identifying faults across this area by selecting individual groups and then fitting planes to them using eigendecomposition. And so this is the northern group. There's about 1,500 faults so far. And I just want to show you a subset of those. This is all map view, and you can see a lot of strike slip faults in this area, just as we would expect from the state of stress. Now, these are those same faults. And if I illustrate it, you can see how nicely the events line up onto planes. And then so you can, fit planes in some cases with a decent amount of reliability. The horizontal uncertainty on earthquake locations is better than the vertical uncertainty. So we might expect that in some cases, the vertical range of the depth range of the earthquakes will be spread out, which could make faults seem steeper than they actually are. in some cases. But what we can do, bearing those caveats in mind, is we can look at the fault orientations on a bulk level relative to what we know about the stress field. And so in this area, we have mostly strike slip faulting. So that's the sort of green colors here. Further north, it's strike slip and normal faulting in teal. Further south, it's strike slip closer to strike slip and reverse faulting. And SH max orientation is fairly consistent at about north 85 east or so. And I've interpolated that with these white lines showing just the largest earthquake focal mechanisms in the background here, and SH max magnitude orientations with the black lines. And here are the orientations of those faults that I identified. And you can see that they're essentially exactly what we would expect to be active in the stress field. These, the faults that are failing are the faults that are the most favorably oriented and that we would expect to fail both naturally and as a result of induced seismicity. So induced seismicity, the wastewater disposal in this area, seems to be just speeding up failure on faults that would have failed anyway, just maybe tens of thousands of years in the future. And so with SH max oriented about north 85 east, we expect strike slip faults striking about 30 degrees in either direction, dipping about vertically, and in some cases, further to the north where normal faulting is active, we also expect an additional set of normal faults striking parallel to SH max and dipping about 60 degrees from vertical. And that's what we see in reality in these histograms as well. Okay, that's sort of a qualitative comparison, but quantitatively, how well oriented were the faults for failure? So these two plots are the same, but the color scale is different. And we're looking at the fault dip versus the fault strike. And they're colored by the pore pressure that would have been required to make them fail at, and the depth of the analysis is 5 kilometers. And so many of the faults, as you would expect, if SH max is about north 85 east, that would be here. Many of the faults are dipping close to vertical, striking about 30 degrees in either direction, and they require low pore pressures to fail, just as we have come to expect. However, there are some kind of on the margins of that would require fairly large pore pressures to fail, in some cases up to about 10 megapascals at 5 kilometers depth. And so that's kind of curious because the pore pressure modeling suggested very little increase in fluid pressure distributed across the state. I mentioned that those pore pressure models are kind of simplistic, so this helps us understand those a little better and suspect that maybe the fluid pressure in the faults themselves is a little higher than the modeling would suggest. But in addition, just from looking at these plots, there's a good chance that some of the explanation for these potentially not so well-oriented faults might be simply just a few degrees of uncertainty in the fault orientations. And I think this is an important concept for industry and regulators to understand, that a fault that looks like it might be safe might actually be sensitive to fluid pressure increases if we account for just a few degrees of uncertainty. And I mentioned earlier that in this case, the depth uncertainty is greater than the horizontal uncertainty in the earthquake event locations, which means that the planes fitted to those events might be steeper than they actually are in reality. And so that could be what's happening here, where we have fault planes that are shown as being very steep, roughly parallel to SH max, but may actually be a little bit shallower and may have failed as normal faults. Because remember, every one of these represents a fault that actually failed. So we're looking into this a little bit more to understand what's going on here. But it brings up an important point, which is accounting for uncertainty. How are we doing for time?
Yes, Eric, you are on time, but if it's possible, then you may take 10 more minutes.
Okay, well then I'll move past the next slides fairly quickly and just point out that there are ways that we can account for these uncertainties. There's a freeware program available from the Stanford Center for Induced and Triggered Seismicity. Ankush Singh, whom we were talking about earlier, was in charge of this program for a while. And it allows you to do a Monte Carlo-based technique to account for the uncertainty ranges in every one of these parameters, the stress magnitudes and orientations, the pre-existing pore pressure, the fault orientations, and so on. And so you can have an idea for how sensitive a fault might be to an increase in fluid pressure in a probabilistic manner. So we can go beyond the sort of deterministic approach. And I'll move quickly here. This is again, going back to that case of the Fort Worth Basin where the Azle earthquakes occurred. Those were here that I showed earlier. I was part of a group that developed a new 3D model of the faults in this area, and then we applied this fault slip potential probabilistic analysis to determine how sensitive all these faults are to increases in fluid pressure due to wastewater disposal. And you can see that some of them, including many underneath the metropolitan area, are red, meaning they're quite sensitive. And so we can compare those to where the earthquakes actually happened. So that's a powerful approach. And I'll just make a quick note that we have work underway right now, me and a couple of people from the U.S. Geological Survey and the University of Maryland, to investigate ways that understanding the state of stress might allow us to improve probabilistic seismic hazard analysis, which has typically been done without considering the state of stress at all. And so in this case, we're looking at a fault in Southwest Oklahoma, and we're considering some fictional cases of how this fault could fail if we allow the stress field to change, or allow the fault orientation to change. And then we're modeling what the change in spectral acceleration or ground shaking would be at either one of two different sites on either end of the fault. And so you can see that the baseline values are shown. If you don't account for stress, the baseline values are these solid lines. But if you do account for stress, you can see that some parts of the fault are more likely to fail first. And you can get to estimates of which direction, or you can predict a little bit better with some uncertainties which direction the fault rupture might occur in. And so the dashed and dotted lines here represent the site 1 and site 2, accounting for some of that information that you can estimate if you know the stress field. And you can see that there's a substantial difference from baseline in site 1 and site 2 in terms of the amount of shaking you would expect at those locations. Okay, moving on, I'd like to end with just a few points about the impacts for understanding geodynamics, specifically the sources of stress when you have improved data sets like this one. Let's see. It's trying to change slides. There we go. As background, there are 3 general controls on the sources of stress in interplate environments. And just quickly, one class is plate boundary interactions, so tractions at plate boundaries between one plate and another. You can also have differences in gravitational potential energy. So, for example, where there's dense lithosphere, that'll bow the crust down above and impose compression in the upper brittle crust where the stress measurements occur. Areas that are rifting, thin lithosphere, for example, will be more extensional, but the margins of those will be more compressive, and so on. And finally, tractions at the bottom of the plate with the, due to drag from the mantle moving relative to the plate can impose either shear tractions or normal tractions, radial tractions to the plate. And so all of these are potential sources of stress that have to be kept in mind. And so a number of studies have been done throughout the world. Here we'll look at the Western US. This is studies by Ghosh and others from 2019. And we can look at these in retrospect by comparing them with the improved stress data sets that we have. And so that the modeled results are in white, and then the observed stress orientations here are in black for this area. And so in this case, these authors are testing various different parameters in isolation. So if you look at just the gravitational potential energy differences, just this class of sources, this is the stress field that you would predict in SH max orientations for those. And of course, they are limited to working with a fairly coarse data set for gravitational potential energy differences. And what you see is a reasonable match in some places. The SH max orientations at the margins of some of these extensional domains, like the Rio Grande Rift here, or the Basin Range province here, are pretty good. In other cases, not so good. And then they've tested, okay, what if we look at just the tractions on the bottom of the plate, the basal tractions? What does that do? Well, it does a little bit better in many cases in matching SH max orientations here, for example, in the Basin and Range, here toward the eastern part or heading into the central parts of the United States, but not so well here in the Rio Grande Rift, for example. And then what happens if you combine those two parameters? Well, it actually looks a lot like just the basal tractions, but it's a little better. Let's see if it's a little better. That underscores the importance of how you pick the parameters. You know, for example, the viscosities of the mantle below and how well it couples stresses to the plate above. But I'll point out that although this accounting for these parameters does a nice job of matching SH max orientations in certain areas, it does not account for the very short wavelength changes in SH max that we see in some places. And that's a function of just how coarse some of the input data are, we think. So, we're hoping that new generations of modeling can improve upon that. And this is another one by the same group from earlier, Lucy, Flesch, and others. Here they're accounting for different factors, gravitational potential energy and plate boundary stresses, not basal tractions. You can see that there's some non-uniqueness between these parameters because they also get a nice fit for SH max orientations here in the western parts of the US. I should note that the plate boundary stresses, plate boundary tractions, are those applied across the San Andreas plate boundary, which is shown by this black line here. Okay, so there's a lot to be sorted out in terms of causes of the sources of stress, and we hope that the new data sets will enable a new generation of geodynamic models. So I'll end with one point that I think is a very important one relative to geodynamics, and that is that stress field is not the same thing as a strain rate field. Strain rate is in some places fairly easy to measure, and so I've seen cases where people have tried to use the strain rate to determine or sort of estimate the SH max orientation. And in some cases that might be fine, but in other cases it's not a good idea, and I'll show you why that is here. Here we're looking at the more stable eastern parts of North America. The stress map on the left, strain rate map from Cornet, Kramer, and others on the right. And the strain rates are very low in this area, on the order of 10 to the negative 9 per year, because this is a more stable part of the continent. But you can see that the strain rate is showing almost opposite patterns of deformation to what the stress field would predict. So the color scale is backwards here, but where we show compressive states of stress, compressive states of stress here, for example, on the southeast part of Hudson Bay in southeast Canada, they're measuring dilatation, so spreading at the surface, and then around that, around the margins of that, a band of contraction. In contrast, in the stress field, we see more or less compressive areas to the west and south. So what's going on there? Well, first, it's important to recognize that the causes of this active strain rate, surface strain rate that we're seeing, is thought to be related to the removal of the ice sheet that used to be here about 10,000 years ago or so. So the Laurentide ice sheet was at its thickest in this area that is now moving upward and undergoing dilatation. And then sort of the margins of that ice sheet were around these areas that are now experiencing contractional strain. Okay, so what's going on here? Why is strain basically the opposite of what the stress field indicates? We think what's going on is that there's just a huge difference in the magnitude of the stresses stored in the crust already relative to what's being relieved by this glacial isostatic adjustment. So if you take, let's say, a depth of 10 kilometers, you assume the crust is critically stressed, you assume hydrostatic pore pressure, which is a fairly reasonable assumption in most places, you would estimate over 300 megapascals of difference between the maximum and minimum principal stresses. in, let's say, this compressive area here southeast of Hudson Bay. In contrast, if you estimate the stress change due to about 10,000 years of post-glacial rebound since the ice sheet was removed at the same depth, at these strain rates of about 10 to the negative 9 per year and reasonable bulk modulus and so on, you would estimate only about 2 megapascals of relaxation of the differential stresses. So that's less than 1% of what the tectonic energy has stored in the crust over geologic time here. So that we think explains the huge difference between the stress and strain rate fields. And I think it's an important cautionary tale here. So I'll end with that. We've talked about the stress mapping, the implications for induced seismicity, and the ways that we hope it improves geodynamic analyses for the future. And I look forward to taking your questions.
Yeah, Jens, it was a great presentation. Thank you so much. There are certainly some questions in the chat box. So I will read those questions out for you one by one, and
Okay.
You may answer those. So the first question is there any critical magnitude of earthquake above which it is considered serious?
As I started to say during the presentation, it depends a lot on the quality of construction in the area. And ultimately, it's a matter of the quality of construction or the type of construction and the surface shaking or the type of ground motion that occurs in that area. In some places, a magnitude 3 earthquake might be, well, let's say a magnitude 4 earthquake in some places could be very concerning. In other cases, may not be, depending on where you are. So that kind of goes beyond just the magnitude of earthquakes into the shaking. Let's see.
And I have also a query, like what could be the possible reason behind happening of the microseismic events in the Permian Basin? What would be the magnitude range? And yes, how the moment generated during the earthquake correlate with the stress in the area?
Right. I'll go back to the Permian Basin. That's an important one for obvious reasons. Let's see. Sorry for flipping through the slides so fast like that, but
not a problem.
The Permian Basin, as this person is implying, is experiencing induced seismicity recently, and this is a problem in some cases because this area is so important for oil and gas development. In the western part here, there's very little population density, so it's less of a concern. But the cities of Midland and Odessa are over here in the Midland Basin. There's been an increase in seismicity near them as well. And the question is, what's the possible reason? It depends on where you are, and this is still being sorted out. We had a magnitude 5.0 earthquake over here in what's called the Mentone area almost 2 years ago. And it is thought, based on some of the papers that have come out, that this is due to deep wastewater disposal. Let's see, in some other places, it's possible that hydraulic fracturing is causing some of the earthquakes. Actually have a better figure somewhere that shows the events better. Over in the Midland Basin, it's also thought to be deep wastewater disposal near the city of Midland. But the bottom line is that in some places, wastewater disposal appears to be the cause, and that is particularly problematic because in these cases we're looking at fluid that may be reaching the crystalline basement, allowing bigger faults to fail. And in other cases, it may be hydraulic fracturing. The question also dealt with magnitude range. The largest is this magnitude 5, but in the area near Midland and Odessa, we're getting near magnitude 4 earthquakes. And there are a lot in the sort of 3.5 range in this area southeast of Mentone as well.
Okay, thank you so much. There is another question from Rashid Shams. He's a student. How we can identify sources or faults sensitive to pore or fluid pressure changes, maybe due to a reservoir or industrial activity?
Right. This is the most difficult part, is estimating, is finding the faults themselves. I'm flipping through this to see if I have a better picture for the Permian Basin, which I don't. Finding the faults is challenging. People use reflection seismic data where it's available. This is being done a lot in the Permian Basin, the Fort Worth Basin, parts of Oklahoma. Since it's the good news is that since it's usually the largest faults that are the most concerning, those are usually the ones that you would be most likely to see in 3D seismic data. There are other techniques that are used in places where seismic data aren't available, like magnetic anomalies, gravity anomalies. These are not ways that you would want to find faults, but they can indicate where there's potential for major faults. And in some places, you can use the same rocks outcropping somewhere else and look at the fault sets in those and sort of get an idea of what the orientations or distribution of orientations are in those rocks.
Thank you so much. There is another question from Dheeraj Kumar, a PhD student. Does structural complexity contributes in deciding critical stress bearing in the region? Yeah, that's an interesting question. There are places where we've shown fairly complex stress fields where SH max orientation changes over short distances, for example. And the causes of these changes are not well known. In some cases, we do think that that structure may play a role. Density anomalies, as I mentioned, can impact the state of stress in an area. So if you have one very area where there's dense zones in the crust, that could impose compressive and extensional stresses that might result in a complex pattern near the surface. Where faults have failed in recent history, there can be a change or a temporary change in the SH max orientation due to just stress relaxation as a result of that stress drop on the fault. So that's possible too, although we would expect that to be limited to not very far from the fault. So yeah, structural complexity definitely may play a role in stress complexity, but short wavelength changes in SH max orientation suggest shallow sources of stress. So those would be shallower density or structural complications. Thank you. The question is asked by Mr. Ravindra Gupta, another PhD student. How many input parameters required for this earthquake regime study?
I'm sorry, for which study?
For the earthquake regime study.
Oh, this is for understanding the style of faulting, Aphe?
I think so. Yes, I'm not sure too.
Let me share screen again. When we're just mapping Aphe, or developing the stress maps and knowing the style of faulting, all that's really needed are earthquake focal mechanisms. In some cases, we've supplemented those with information about what the style of active faulting is in that area from quaternary fault maps. If the question is about parameters needed for these probabilistic geomechanic analyses, the parameters needed are shown here, basically. You just need to know the three principal stresses, or Aphe value and a vertical stress, pore pressure, fault orientation, and coefficient of friction.
Thank you so much. This question is asked by Mr. Mukesh Kumar Das, PhD student. What type of magnitude we can expect from hydrofracturing, and which type of signature gets recorded in a seismogram?
In the what program?
In seismogram.
Right. Well, I'm not sure that there's a limit really to the size of earthquake that you can have from hydraulic fracturing. The limit is imposed by the size of the fault. If it's a critically stressed fault and it's a large one, you could potentially have a large earthquake. I think the largest earthquakes I'm aware of related to hydraulic fracturing have occurred in Western Canada, and I think those are in the high 4s and low magnitude 5 range.
Thank you.
I should mention the Pohang, South Korea earthquake, which I think was a 5.4, and that was enhanced geothermal development. And of course, that site has been shut down after that earthquake, but it's a sizable earthquake.
Okay, thank you. There's another question from Rasha Shams. Is it possible to integrate stress-related information for developing seismic hazard map and further into PSHI?
Yes, that's what we're testing this idea out, and I think it is possible. The ways that it'll impact PSHA and seismic hazard maps are not yet fully clear, but there's several potential ways that it could. For example, knowing the relative stress magnitudes of the style of faulting will give you an idea of what the focal mechanism might look like for an earthquake in an area, and that'll affect the style of shaking that'll occur. Here we're testing things that are a little more basic than that with, in this case, there's one fault that has several different segments. In the stress field, you can see in this particular test, in this particular case, this one portion of the fault, this one segment would be better oriented than others. So you would expect that there's a certain percentage higher probability that the earthquake would localize on this side as opposed to this side. And it might propagate in that direction, but it's a probabilistic matter. And so, so that's a localization issue and a directivity impact for directivity. And so on. So yes, this is possible, and we're just testing it out from the, doing some of the early tests on this. This is led by Konstantinos Francis at the University of Maryland. If you have more questions for him. Okay.
There's a question from Partho Pratim Mandal. What kind of safety framework are there to minimize induced seismicity? A stress map would help to set those safety criteria, I believe.
Right. The stress map is helpful in a few ways. For example, if you know the faults in an area, as someone was asking a minute ago, you have an idea of which faults might be sensitive. You might not want to inject anywhere near those ones, but there are other faults that might have very low sensitivity to fluid pressure, and so those would be fine. There are, beyond understanding the stress information, there are a number of other important frameworks for estimating hazard and risk associated with induced seismicity. I didn't get into any of those here. I guess I should, because they're fairly complex topics, maybe I think I may have a figure for one of these. No, I don't. I'm sorry. But the Stanford Center for Induced and Triggered Seismicity has been doing a lot of work along these lines. And one of the techniques is the use of what's called the Seismogenic Index, where if you see the first few small earthquakes in an area, you can use that information to estimate what the seismogenic potential of that area is if you increase the fluid pressure higher. So that's one approach that's been used. There are approaches where you can take into account population density in an area, the shallow seismic velocities and those sorts of information, and estimate what the largest earthquake a particular area. See, you could approach it from several different ways. Ryan Schultz has a paper on this very recently, also from Stanford, where you can say, let's say, we want no more than 1 million people to feel an earthquake with this much shaking, and then you can step backwards from that and say that at this particular site, if you start to see earthquakes approaching this size, you need to stop or change your operations because you're about to impact that many people. So the details for that are provided by Ryan Schultz, and I think one of the papers is in Science quite recently.
But that would need a very dense network of stations to see the direction of the earthquake coming.
I think what I mean by that is not so much of the direction, but if you're looking at one particular site and you have information about the population density, the seismic velocities near the surface, and so on, you can take that site and then imagine what the ground shaking would be, in a radius around that area. And so if that makes sense.
Yeah, it does. Okay, I think that is all in terms of the questions from the audience. So I would like to thank the audience for the wonderful questions, and Dr. Jens-Erik Snee for the answers, for the detailed answer that he provided for all the questions. And on top of that, I would like to thank you from the bottom of my heart for taking time from your busy schedule to be the guest speaker at this webinar. And I certainly think that your presence and the words and the knowledge that you have shared with us will certainly help us to magnify our knowledge about the stress maps in the US and the world, and the earthquakes that might be happening due to the reservoir induced seismicity, and also the microseismic events that you have talked about regarding to that of the Permian Basin. And also regarding the stress maps, how it can improve the probabilistic seismic hazard value in a region. With this, I think I'm very much thankful to you for sharing your knowledge with us, and through some wonderful slides that you have prepared. Thank you so much.
Thank you. Thanks, Partha, and thanks to the audience for some great questions. It was a pleasure to present to you all. Too bad it can't be in person, but maybe one day.
Yeah, yeah, sure. Actually, like there are several scholarship and the fellowship through which you can come. Like last year, in 2019, my professor from Texas has visited me on Fulbright fellowship as a
nice.
as a Fulbright chair professor for the period of 4 months. He and his wife was here in the campus and was staying and was actually contributing to the research that I am undertaking with my PhD students. So that was a great opportunity for all of us. I think there is one more question from one of the audience. He's actually insisting upon it. So he said, I read somewhere ambient noise tomography used in induced seismicity studies. Do you think it would be a good idea to use here? Because in that case, we need not to know the source information.
Yeah, this is a little bit outside of my knowledge range. I think what this is getting at is about seismic velocities near the surface and what you would expect in terms of shaking. For that, I think you would need to know, or it would be helpful to still know source information. I guess I'm not sure how to approach that question. I guess I'm just not familiar with that paper.
Okay, not an issue. Actually, okay, that is fine. So yes, that is all. Thank you so much, and I hope we will meet again. And certainly, we will keep on be in touch with you through emails. Thank you so much.
Thank you. Have a good evening, everybody.
Bye.
Bye.
Bye.